Good afternoon, good evening, good morning, everyone. Welcome to the Stratasys webinar on simplifying part validation for aerospace production with GrabCAD Print Pro. We're really excited to spend the next half hour, 45 minutes, talking about some ways to streamline the process of validating parts. There's a lot of different steps along the way from taking a part from development to production. And we know those steps include parts where you need to validate the part requirements. And so today we're going to focus on some tools in those processes to help you evaluate and improve the quality of those parts based on the actual build. So my name is Victor Gerdes, and I lead software product strategy and planning. And I'll be joined by Patrick Price.
Hey everybody, I'm Patrick Price. I'm a senior applications engineer on the aerospace team. I've been with Stratasys for a little over 10 years now, working with our aerospace customers to help solve their problems using additive manufacturing, and really excited for us to present these modules to you because this is exactly what I've been hearing from you, our aerospace customers, over these past years. So hopefully we have something that is based off of your requirements that you've given us over the years and can help you along the way. And then I'll turn it over to Rashid from Alpha Star.
Hi, I'm Rashid Miraj. I'm the Director of Technical Operations at Alpha Star, which primarily means that my focus is to make sure that the company is in the appropriate alignment with the needs of industry, needs of the DoD, as well as the automotive industry, power energy communities. Just making sure that our development of our tools are meeting the challenges that are out there and making sure that we have the appropriate validations, the appropriate documentation to justify their value to those end users.
Terrific. Thanks, Patrick. Thanks, Rashid. Well, we're going to kick this off by just talking a little bit about these tools that we're going to talk about, how they've come about. So many of you are familiar with GrabCAD Print. We introduced GrabCAD Print Pro earlier this year, which is an advanced version of GrabCAD Print to help you create more accurate parts more quickly. And so today, the part of the creating more accurate parts, we'll be talking about a capability called Accuracy Center, which is built into GrabCAD Print Pro. And Patrick will talk about Accuracy Center and how it can help you create more accurate parts. But we're also very excited that GrabCAD Print Pro represents the openness of the GrabCAD platform and allows the ability for third parties to create plugins. And so Alpha Star is one of our GrabCAD software partners that has created a plugin into one of their simulation applications. So these are both Accuracy Centers built into Pro, and the Alpha Star simulation is a plugin. So so with that, let me ask Patrick if you can talk a little bit about Accuracy Center and sort of how you'd use that and where it fits in the production validation process.
Sure. Yeah. So like Victor was saying here, this is integrated into GrabCAD Print Pro. This is a Stratasys product. So the first module we're going to talk about here is what we call the Accuracy Center. And so what this module does is it takes a scan of your printed part and it compares it to the CAD model and then scores the accuracy. So you can see on the images to the right, it provides a nice color map, score, and a histogram to show the accuracy of your printed part as compared to the CAD model. And what I think is the coolest part of this module is actually what we call the WAM, the Warp Adapted Model technology. And so based off of this histogram and this accuracy score that we have, we can actually pre-warp the STL file based off of the comparison to greatly improve the accuracy of the next part. So as long as you're holding all things constant, you're building the part with the same material on the same machine in the same spot, we can see a great improvement in the accuracy of the part. So on the bottom right there is our first iteration. That's just taking the CAD model as is, and then printing it and scanning it and comparing it. And so we have some deformation due to the thermal effects. Just kind of the nature of the process is we have some areas that shrink based off of the geometry. And so for these really complex parts, we're able to correct that deformation and, like I said, essentially pre-warp it. So when you build it again, it essentially warps into the correct shape. And so you can see the difference from the bottom to the top. That's, again, holding all things constant, using the same tolerance spec to generate that heat map. You can see that we have a lot closer accuracy to the desired CAD model there. So just a visual representation of the improvement that we can get.
Terrific. Thanks. Thank you, Patrick, for that.
And then, yeah, so getting into some more details on how it actually works. So within Print Pro, we're comparing the scan to the CAD model. So you can use any scanner. We don't have a preferred vendor for this. The better the accuracy of the scanner, the better results you're going to get when you're bringing it in and pre-deforming, because we just take in the mesh file for the comparison. And so the scoring gives you a quick view of how accurate your part is, and it demonstrates the improvements for the next iteration. And the histogram and the heat map also give a nice visual of the accuracy in addition to the score. So we can generate a WAM model to improve the future prints of the same geometry. And again, all this is done within this GrabCAD Print Pro module. So you don't need to do this in any external software. You don't need to try to pre-warp the geometry in CAD on your own, which tends to be very difficult unless you happen to be an expert at CAD at using the deform tool, which I am not. So it just makes life a little bit easier for trying to correct that. And where we see this especially valuable is when we're getting into these production parts, right? So you print one part, you scan it, you make the changes, and then you can print your next 10, 100, 1,000 parts, and you're going to get this improved accuracy for every single one of those down the road. So it makes a lot of sense for production, which we see a lot of our aerospace customers getting into. And so with that, I'll turn it over to Rashid to talk about our build simulation plugin developed by AlphaStar.
Yeah, thank you. And just want to say that feature you described is really cool. Congratulations. Before we talk about what our value add is, I'd like to give a little bit of background on AlphaStar. We've been around for a good while, about 33 years, and have a deep history into advanced composite materials. So a solid understanding of polymer matrix composites, ceramic matrix composites, metal matrix composites, and using that to understand or develop physics-based simulation tools for both advanced materials and advanced structures. And that incorporates virtual manufacturing to understand what happens during the process of building, and then looking at that virtual part, subjecting it to service loads, and seeing how it performs. So you have that constant now digital thread of where the part is, and is it on track while you're designing it, while you're fabricating it, and while it's being used. And we've been providing this services to aerospace, DoD, automotive, the energy industry, as well as academia. And our credentials are based on over 430 peer-reviewed journal articles of our work, 5 technical books that have come out of it, and close collaboration with some of the best laboratories and companies in the engineering sphere. And our credentials are not only a couple of R&D 100 awards, I think 2 NASA Software of the Year awards, but I think the one we're most proud of is the Columbia Accident Investigation Board Award, where we were tasked with doing the forensic analysis, understanding what happened to the Columbia Space Shuttle once the leading edge was struck and there was damage to the wings, and what was that damage, and then with knowledge of that damage or predictions of that damage, what was the consequences of reentry. Everything we know forensically about the Columbia accident is based on the analysis that was done with our software. So what is our contribution? First of all, the GrabCAD Pro being a really great tool gives you that ability to set up your problem once you know what the material system is, once you select your build platform, you have your understanding of your CAD file, your geometry, selecting a particular build orientation. That tool gives you the full build path simulation or G-code on how to go forward. And so it allows you to do that heavy lifting before you, go through all the problem trying to figure out how to build that part yourself. That problem is solved directly and gives you a chance to really simulate and generate the tool path going forward. What do? What we do is an extra set of eyes, basically, to look at that problem. For additional, very limited computational time, you get first a way to assess the quality of the tool path, and I understand GrabCAD Pro is already doing that, just to give it an extra set of eyes to overlook the problem again. So not only say on the boundary of the build, but internally, depending on the complexity of the part, we can assess gap assessments, detect air gaps based on that tool path, based on the geometry, and give you insights on whether or not that would be a logical build to go forward with. Allow you to say, maybe I should go back, take a look at this tool path a second time, maybe make some changes so that the not only the aesthetics would be in place, but depending on the size of the gaps, what's happening, are you impacting the finished product in terms of its performance? So again, an extra set of eyes to allow you to make that judgment to, again, reduce trial and error fabrication. The other component would be what we call our thermal analysis, thermal build analysis. Again, understanding what the build plan is, the G-code, build path, all of those factors coming together, all the parameters that are driving this build process. What are thermal gradients that come into play? And then with the material selected, what are the consequences of those thermal gradients that come into play as related to the build plan? With that, we're able to identify hot and cold regions and that impact on the part, and is that resulting in additional anomalies that need to be addressed. So with the output of that, again, think of it as a flashlight, shining on potential anomalies ahead of time and giving the end user the opportunity to say, is this a suitable part to be built, or should we go back to revisit this problem in terms of adjustment of parameters, either taking simple steps or more complex steps to address this problem. And if everything is on board as it should be with GrabCAD Pro, you can go straight to the build. And we've just given you an extra set of eyes saying things are on track, don't worry, everything is good. So what are those defects that we're talking about? We can start with those hot and cold regions. As you can imagine, in the build environment, it's a dynamic environment. You have not only the process parameters dictating what's happening with the airflow, you can have within the build environment different areas of hot and cold, and that can impact the overall build quality. So if the part gets too hot, particularly if it's very thin, you're going to have warping and rippling on the skin, and it's because it's not being exposed to enough airflow, or where it is in the actual build plan, it's just getting the depositions or maybe laser strikes that are coming too fast, so everything can heat it up more than it should be. And in the same way, the opposite side would be if you have a very thick part, it could be curling because it's cold. It's not really getting the airflow it needs. And in this case, there's time for warpage and curling of the parts. And again, it's deeply connected to not only build time, but the selection of materials and the tools that is allowing you to capture all of that information to assess what would be happening. So as you can see, again, continuing with the discussion of thermal build analysis and identifying hot and cold regions. On the left side, you can see here a build platform where we're working with the Ultim 9085 from the F900 machine. And in this case, we're talking about very thin parts. Again, where they are in terms of that build environment, in the warmer regions or the colder regions. And in the case of the small triangle on the right-hand side, we're set to see the curling effect because the part is a little bit too cold. And it's almost like the story of the Goldilocks. This barge is just right, or this barge too cold, too hot, or just right. We're helping you see that in a very simple and effective manner. If you look in the methodology in the central imagery, you can see that we're predicting the thermal gradients, we're understanding what the temperature variation is going on during the build, and we're able to correlate that in terms of what the material selection is to see how that impacts it. So with your knowledge of the dynamics of the environment, knowledge of the material and the build plan, you can now see what the potential consequences of that are in terms of build quality. On the right-hand side, we're showing what the simulation does. Again, that assumption or assessment for what is warm, what is too hot, too cold, what is just right. We understand that with the too cold, we'll have the residual stress. We're going to have, in this case, the corroding and warping. And the same case with a too hot environment, so additional deformations that come into play. And so here the end user would have the opportunity to employ what we would call best practices, understanding what is going on, right? And then making the best judgment, the best conclusion on how to move forward. It can be as simple as, in the case of too hot or even too cold, adjusting the position of the part within the build site, recognizing where it is in terms of the build path, where it is in terms of depositions or laser strikes to either overheat it or there's enough time or movement of the head to allow it to have a chance to cool. So those are very simple level 1 fixes. A level 2 fix might consider modifications to the part itself. The idea of adding more mass to absorb heat as necessary, or possibly potentially thinning the part as necessary so the conductivity of thermal heat can pass through and really address that too cold problem in a different approach. And then finally, a higher level decision making best practice would be looking at the actual parameters in greater detail and looking at how you can optimize the selection of those parameters to come up with the best approach to address those issues of hot or cold, the thermal gradients that are impacting the final quality value in the finished part. And so here's an example of a very large part. And this one's interesting because in the case of the triangles, you can shuffle them around. But in this case, for this large hubcap, there really isn't that much movement opportunity for the part within the build environment. So again, maybe you have to go to the next higher level build practice solution on how best to adjust this, or even above that to the process parameters. In this case, we're noting that there's a stagnant air, which is impacting the actual hot and cold regions within the part that's being built. With simulation, you can see exactly where that is taking place. A very simple analysis that's now would be a part of tools available to GrabCAD Pro end users. And with that, they can then say, hey, what's the best way to deal with this? And in this case, it's an adjustment of boundary conditions, which allows you to not only get a better prediction of the results, but to drive the part into the direction that you'd like it to go in terms of final build quality. We talked earlier about air gaps and how not only is the quality of the part affected by the lack of material, lack of deposition, lack of placement of materials on the boundaries, but also internally in terms of the complex part. As you can see here, as the material, in this case, deposition, is laid down on the edges, the movement of the tool path can lead to little gaps, and certainly that could impact the aesthetics, the final quality, the final net shape of the part. But depending on where it is or how the part is ultimately used, it can definitely impact performance, particularly say for some of those areas that are noted on the interior of the part itself. So this tool allows you very quick and fast to get an assessment of where those air gaps are and how they are impacting the build quality. And again, GrabCAD Pro does this. Think of this as a second pair of eyes to give you that additional confidence that everything is in the right direction. And then notably, this tool also allows you to say, is it going to impact the strength, performance, and final build? How does it impact walls and other critical areas within the part? And so it gives you the feedback on whether you need to go back and revisit the tool path, or if you have confidence to go forward with the build as is. The long-range goals are to not only have that build preparation, that GrabCAD provides you, and similar to more detailed material modeling, that we take that information from GrabCAD and do a really detailed assessment of the material model, understanding the impact of temperature on modulus, understanding elevated temperature properties versus cooler properties. All of that really detailed understanding of the effect of the materials involved in the build, and complementing that with the thermal physics, the temperature distribution that we just talked about, that's going on with the part related to key codes and parameters that come into play. How does temperature change as a function of time? And then also the build path, toolpath errors that we talked about, understanding what those gaps are and what are the consequences of all that gaps, all those problems. All of that information is then bundled into a analysis, a mesh, so there can be thermal structural analysis. Now, this is something we're building to. It's not necessarily part of the tool set at this point in our work with GrabCAD Pro, but it's something we're working towards. So at some point in time in the future, that full capability of understanding thermal and mechanical defects and the effect of defects on print quality will be made available to this community. And with that, I'd like to pass it back to Justin.
Awesome. Thank you. Thank you, Rashid. Thank you, Patrick, for going through that. Yeah, so if you have any questions, you can type them into the Q&A panel, and we'll step through those questions and get you some answers. So we got a couple questions that have come in already. Maybe, Rashid, the first one for you is, what materials have you tested with the simulation capability, or what materials do you currently support?
In terms of this relationship on this plugin, we've worked with Alstom 9085 and with the Nylon 12CF material systems, and we're constantly adding to that in our own database. We have a bulk of stuff, but in terms of making available to the GrabCAD Pro community, those are two materials that are available right now, but again, more will be coming down the line. Will be available very, very soon.
Gotcha. Okay. Good. Another related one is Stratasys introduced this capability, OpenAM, and the question is, how can I leverage this tool for OpenAM materials, and what material information do I need for that?
The use case for OpenAM material is very strong, as it allows users to assess the behavior of material that they don't have much experience printing on a Stratus machine. But because this OpenAM material is not in our database, the user would need to add those thermal properties of that material, input them into our tool to get the same results that you're seeing for the known material system. So if a user can provide density-specific heat conductivity, they're good to go, and we'll be able to take advantage of what's out there with OpenAM.
Okay, terrific. So if there isn't a material that's been that you guys have worked on, or Stratasys, that I can use OpenAM, and as long as I can find the material properties, I can apply it and use the simulation model that way then. Okay,
specifically the thermal properties.
Gotcha. Okay. So one, Patrick, for you, which is with Accuracy Center, do you need to scan it every time to correct it?
No, I mean, most of the time your parts are going to be, within the desired tolerance for the applications that we see in aerospace. It's more for either those really high-end applications where you need even better tolerance or accuracy than what our machines offer, or you have a complex part where you have different thermal masses. You have a block of material over here, and then it's next to a thin wall, and so you get some maybe not predictable deformation, or something that you're not expecting. So it's really, this tool is for if you need an improved accuracy, or if you're seeing deformation that you're not really expecting. And kind of like what Rashid was saying, if you don't want to actually go in and change your model, this is a tool to help correct for that. So for example, like composite tooling, we've seen some large composite tools that customers are trying to do where they're trying to hit a much higher accuracy than what our machines are spec'd and capable of. And so this would be the perfect tool for them to be able to use to generate a WAM model, correct for that, and then get a nice accurate tool that they can continue to use for production.
Great, thanks for that. Another related, sort of similar to the one that was asked for Rashid, is there any limitations on which Stratasys printers or materials the Accuracy Center works with?
Currently, we've worked with the F900s. I'd have to check back with my colleagues to see what additional platforms are available. We have our tool set capabilities are solid with FDM technology and SLS technology. So it depends, again, what the platform is and what you're trying to do. I'd have to check on a case-by-case basis. But right now, F900 is working very well.
Okay, that's a good one because that's a pretty popular one for the aerospace applications for sure, is the F900. Patrick, in the case, what would be the answer as it relates to Accuracy Center and how that applies to the different printers and materials?
Yeah, so we're process, material, machine agnostic with the WAM model and the Accuracy Center. It can compare, just like any scanning software, it can compare and give you that heat map. And then as far as the WAM model, it's really just looking at that comparison and correcting based off of that. It's kind of like I said when I was going through the slide there, you have to maintain the consistency in the process. So for example, if you're building a part out of Ultem 9085 and it warped and you build it out of ASA, that's obviously that's an extreme comparison, but you have to keep the material, the placement in the machine, and the machine constant. But we're agnostic. It can be our SAF technology, which we have applied this to as well. So it really works for pretty much anything we offer.
Okay, good. All right, we answered that one then. Another question is, in the slide that you showed, there's a number, there's like a number score for each one of those. What does that represent?
Yeah, so that's our print accuracy score. So we take what the capability of the system, so our published accuracy that we have in all of our machine spec sheets. And so if we have 100% of the points of the STL or the mesh file within that accuracy, your print score would be 100. And so if we have a low number of points within that, we're saying that it's a low print accuracy score. So it's really a comparison of the model to what the printer's capabilities are. So an accuracy score in the 90s is very good. Obviously in the slide you're showing towards the bottom in the 20s is not great. So the higher the better is what we're looking for there.
Gotcha. Okay, thanks. Rashid, we've got one for you, which is how long does a simulation take?
Well, it just generally depends on the size of the build and any requirements regarding resolution of the simulation itself. But generally for the air gap analysis, probably 2 to 5 minutes. And for thermal analysis, and again, depending on fidelity of the model, can take anywhere from 30 minutes to about an hour. But again, fresh set of eyes, chance to really see what's going on, and sure beats 3 to 4 hours of a build and lost material time and personnel time.
Right. Yeah, that's a good point. Just sort of I guess sounds like what you're saying is the benefits of you're weighing the time for doing the simulation versus the time for running a build and the material and the time that is used for that build. That I guess ounce of prevention is worth a pound of cure in terms of doing the simulation up front.
Yeah, not to mention the setup and cleanup.
Right. So actually, that's go ahead,
Victor. If I could just add to that really quick. Yeah, we've had lots of customers that I've worked with. They essentially want to virtually print their part before they actually print the part. So I think kind of hitting on that note of, yeah, the simulation might take a little while, but as far as simulations go, that's still very quick. But yeah, not to lose a day-long build and that material, that machine time. From the feedback that I've gotten from our aerospace customers is they're more than time if they can get a successful part out of it. So just a little addition to that.
Right. Yeah, that makes sense. That kind of is a good question that sort of pulls to both of you, which is we're talking about validating a part, and there's two different approaches. One, simulation, the other is printing it and scanning it. And the question is maybe to both of you, how can you envision using these tools together? You know, as an engineer, when would I use one? When would I use the other? Could I use them together? You know, do they both help me, or is it one or the other?
Do you want to go first on that?
Sure. Yeah, I would definitely say that they're both applicable, even to the same part. So you could simulate it beforehand to ensure that you're not going to get a complete build failure, right? So you could see that through the AlphaStar program or module platform that if it peels up and you're going to get a failure, you could maybe move it around. You could add anchor pins, something to help prevent that total failure. And then even if you do still get a little bit of deformation and maybe it's a really complex part, then we could go ahead and scan it, do the WAM model, and go back and build it again. So yeah, I definitely see these being complementary to each other.
Yeah, I would just add first and foremost that WAM feature is a really great tool. Really, really, really nice capability. You guys did your homework well on that one. Where we would come in is, again, more on the thermomechanical analysis. So not only are you predicting the build quality, but you're recognizing, predicting based on the defects that arise, the process, the G-code, all that information, thermal model, thermal distribution. When you kick in the thermomechanical structural stuff, you can see and predict distortions, and you can understand where is the shrinkage, where is the warpage, what's going on, how is that impacting the build, which is what you guys are doing already, which is pretty cool. And then if that's the case, you could then do what we call jig shape analysis. So you can take advantage of where it's going to be shrinking, where it might have expansion and things like that overall with the build quality, and kind of optimize towards that to take advantage of that. That's how we look at it. But as I said, you guys have already got that to a certain degree. Ours would be that, again, additional set of eyes. I could tell you, is it going? But the good part that we could throw into that, if you went with the full tool set, thermal structural analysis, is predicting what is the performance of this part as it is as built. What is the behavior, performance, is meeting? Not only is it meeting the net shape or all the concerns, is it performing as expected? And if not, pass it back to the designer and say, hey, let's look at this digital thread one more time and see how can we improve it.
That's a really good point. Is there's dimensional accuracy, and then there's the actual quality of the build, and the quality of the build is going to relate to the part performance. And so it's using them together as you're getting the assessment of dimensional accuracy, and then the quality of the build for performance. So really, in that case, it's kind of a Venn diagram. You're going a little bit further than what Accuracy Center does. Super helpful. Another related question: a lot of the folks that are on this call, probably in aerospace, might be using Insight with today when they're using Stratasys FDM printers. And so a question is, can these tools be used with Insight? And maybe, Patrick, you could start by thinking about how that may or may not work.
Yeah, so as far as Accuracy Center, yes, you can use Insight. So as far as the comparison tool, you're taking the scan and comparing it to the CAD model within GrabCAD Print. So as far as the actual comparison and the plugin, that is only in GrabCAD Print. But if you want to process your part in Insight and build it using, your company's parameters that you've deemed are the best, or just have that ability to control more things, you can absolutely build it in that software and then just do the comparison in the Accuracy Center. That module does have the ability to export the WAM model as well. So you can export that that CAD file and then bring it back into Insight and process it again with using your WAM model. So yeah, it's a little more cumbersome to switch between the softwares, but yes, you can use Insight with that.
I would just add that the capabilities of our plugin are available through the license of the GrabCAD Pro suite. So once you have that, those licenses become available to you for what we have and what other third-party softwares have. In terms of working with Insight, it would be from a perspective of standalone interaction. The fact that you can generate formats and file structures that we can use, and then kind of chase that thermostructural stuff that we were talking about. But the simplicity of use is within the plugin in the GrabCAD Pro perspective. But yeah, we'd love to work with Insight too, and certainly have. If you don't mind the sneaker net as opposed to the internet, you can just kind of move the files back and forth as necessary.
That's helpful. That's helpful. We're going a little bit long, but we've got another question or so that I just see come in. So, and this is Patrick, and so it's assuming the WAM models are single printer specific. Do specific WAM corrections from a specific scan of a part printed from a specific printer offer any insights into an unintended into an intended WAM pre-scan for printing on a different or otherwise identical printer? So great question. It sounds like, you know, I have two F900s, two F450s. Yep. I printed on one, I scan it. Does that give me any insights onto the other printer?
Yeah. So yeah, as far as, you know, if you're building on an F900, do an F900, yes, that scan that you used on 900 number 1 would be valid for 900 number 2, again, keeping everything else constant. Where we run into more difficult is if you're going, say, from an F900 to an F450, where in those machines, the oven characteristics are slightly different. Some of the extrusion temperatures and even the oven temperature itself is slightly different to optimize performance. But yeah, if you're using the Stratasys, you know, printer to printer of the same model, those are very consistent, very repeatable. So yes, you'd be able to do that.
Cool, excellent. Okay. Well, I think we're getting toward the end here, so I think what we'll do is, I do want to say thank you everyone for attending. And I know that there'll be some who are here live and some who will listen to the recording, which is great. Those of you who maybe didn't catch the whole thing, you'll get access to the recording on demand at some point in the future. And I just, again, thank you for attending. And if this is a topic that's interesting to you, or there are other topics that you'd like to be discussed, we'd love to do that. So let us know. And so the way that you can let us know is you'll certainly be getting a follow-up email from us that has information about the recording, and that'll give you a chance to reply back and give us feedback on either this webinar or something you'd like to hear in the future. Alternately, you can also contact us directly. My name is Victor Gerdes, but my email is victor.gerdes, G-E-R-D-E-S, at stratasys.com. And maybe Patrick and Rashid, you guys could share your contact information to follow up on.
Yep, mine's the same format, so patrick.price@stratasys.com.
And mine is rmiraj, M-I-R-A-J, at alphastarcorp.com, or just visit our website at alphastarcorp.com and hit the contact page, and you can reach myself and many of my colleagues.
Terrific, terrific. Well, thank you, Patrick. Thank you, Rashid, for joining us and presenting, and thank you all you folks who listened in, and look forward to having another webinar like this in the future. Thank you. Bye-bye now.
Thank you.